Till the end of April, yeah.
The end of April, so...
Just have maybe you take the mic as well.
Yeah.
Okay. And so the SNOKE will be here until the end of April, so and he will give a couple of more talks. This one we have chosen to be the first one, as it's about foundations of quantum mechanics. But at any point you can talk to him during the next weeks. So he's a distinguished professor at the Department of Physics and Astronomy at the University of Pittsburgh, where he was also a professor before this distinguished professor since 2008. His main research, if I may say, is maybe solid state physics.
Solid state optics, yeah.
Solid state optics. He had several guest appointments as a guest scientist at MIT, Yale, University of Brisbane in Australia, University of Otago in New Zealand, and so on. He's also elected fellow of the American Physical Society, and now I'm in the division of condensed matter physics. And I'm citing for his pioneering work on the experimental and theoretical understanding of dynamical optical processes in semiconductor systems. Good. Very distant from my own field. And he has published several many papers, but several books, which I mentioned either as he was an editor or an author about Bose-Einstein condensation for Cambridge University Press, Bose-Einstein condensation of excitons and biexcitons and coherent nonlinear optics with excitons, also Cambridge University Press, solid state physics, essential concept, electronic, a physical approach, universal themes of Bose-Einstein condensation. But the last one, which is in press, is something which relates, I guess, to your talk as well. It's Interpreting Quantum Mechanics, Modern Foundations, again with Cambridge University Press. So, welcome, and we're looking forward to your talk.
Okay, well, thank you. I'm really looking forward to being here, and this hopefully will start a conversation, and I would really be happy to have people come and talk to me if they disagree with what I'm talking about. This talk is going to be maybe about half philosophy and half actual science and equations, so I think this is the right place to talk about that. But one of the things I probably will not do is be very fair to a lot of different interpretations of quantum mechanics. I'm going to sort of summarize them very, very quickly. So if you want to come and talk in greater detail, just set that up and let me know. This is based on a couple of papers that have come out in Foundations of Physics, and it's really ongoing work. So what I'll do here is probably the first half of the talk almost, I'm going to really just present my general approach to quantum mechanics. Then I'll introduce my specific proposal and discuss it in relation to some of the other attempts on this. So let me start at the very beginning, and I apologize if a lot of this is really familiar to you. So in general, it's good to set the table with kind of their general perspective, but I know a lot of this is very familiar to a lot of you here. So I'm going to group interpretations of quantum mechanics into two groups, probably somewhat unfairly. But the first group I will call positivist. And they're not the same as each other. They're quite different in different ways. But all of them, I would say, really say don't ask certain questions. There's certain things that are simply not proper questions to ask in quantum mechanics, so don't ask that question. The second category, which I call real-world narratives, is ones that, to some degree at least, try to say, what's really going on in the real world, and to ask many of those questions. Now, of these, we can distinguish between Copenhagen and all of the other ones. In that, in the Copenhagen interpretation, the wave function would be treated as what's called epistemological, that it's really just a statement of knowledge and doesn't have any ontological reality. On the other hand, the rest of these have what you can call a reified wave function. That is to say, the wave function is really something real that we can think of as a physical entity, exists whether or not we're looking at it. Now, of these, two of them I would say are ruled out by experiment. One of them I don't have to tell you about. You have a local Nobel Prize winner. Local hidden variables theories have been experimentally ruled out by EPR type experiments. And a second category is one that actually I find a lot of physicists have belief in, but actually is ruled out by the not only the experiments, but by the theory of quantum mechanics, which is what I call unitary spontaneous collapse. And this would be sometimes what you could call the physicist's intuition, that if you look at Copenhagen and you say, well, when we know something, then you get this collapse of the wave function. Well, actually, the only thing that's important is that it's interacting with a large system. And brains are only important because they're large. And there's nothing specific about knowledge. And therefore, any large macroscopic system will have the same effect as knowledge. Well, that would be a unitary spontaneous collapse. That would basically say, given quantum mechanics as we know it, we get collapse just if things are large enough. And that is actually not possible in unitary theory. You have to have something non-unitary for collapse to happen, as I'll talk about. So I'm not going to be really fair to Bohm and Kramer. I will talk about many worlds a little bit. And what I'm proposing can be called a non-local hidden variables theory or a non-unitary spontaneous collapse. So let me just take a couple steps back and talk about my general approach then. So my first premise is simply that field theory, or many-body theory, as it's called in condensed matter, is the proper theory of quantum mechanics. And so any philosophy needs to be cast in the language of that and not just in simple Schrodinger equation with particles. And so that's a general approach that I would say. As such, if you take a many-body course or quantum field theory course, you learn in the first week or two that particles are simply resonances. And so you can think of them as resonances in the wave amplitude. And they're not little Berry balls flying around. And so in quantum field theory, one would say that the particles are epiphenomena. They are derived from a deeper underlying theory. Another thing we learned from field theory is that fermions and bosons are quantized essentially the same way, only with a change of sign. So this would be a boson commutation for the plus and a fermion commutation for the minus. That says to me that whatever we say about fields and waves for bosons, we should be able to have a similar language for fermions. It doesn't make sense to say that the field is real, ontologically real in the case of bosons, but it's only a knowledge wave in the case of fermions. Because they're really the same thing, only just with a different sign. And so it stands to reason to treat them on equal footing. Well, then if you buy that, then the next thing you can say is that, well, classical waves are simply high-amplitude boson waves, and we see them all around. So, for example, you could be on the ocean and have a big water wave, and one might take the position to say, well, that's not really real. That's really a macroscopic number of bosons in a coherent state, macroscopic number of phonons. That would be mathematically correct, but it seems artificial to insist on that and not just say that the wave is really a real thing. And so if we think about what we mean by reality, sitting on a boat on top of it seems pretty real. And so I would argue that classical waves are ontologically real, and therefore boson waves are real. And therefore, since it's only a sign change to get fermion waves, we ought to treat fermion waves as real in the same way. There's important differences, of course, which will come up. And finally, of course, you can convert them into each other. you can convert bosons into fermion pairs back and forth. And so again, to say, well, one of these is a knowledge wave and the other one is ontologically real, it doesn't really make any sense. Question? Yeah?
But how does this go around the usual story? Let's say you have a Mach Zehnder interferometer, and you want to try to interpret what's going on as waves, but if you detect just after the first beam splitter, you never get half clicks, which is what you would expect.
You never get what?
Half clicks. You don't get half amplitude.
Right, right.
Which is what you would expect if you are doing a wave interpretation. So how does...
Well, let me be very clear here. I'm not saying that everything is classical. All right, so I'm saying that quantum waves, the wave function of quantum field theory or many-body theory is ontologically real. Okay, that wave function has these commutations in it. Okay, and this commutation relation forces that you can't get a half click. So what happens is, of course, in the classical wave limit, when n is very large, the non-commutation of the operators becomes negligible in coherent waves. And so you can treat them as classical and say everything commutes with everything, and therefore we can have half things and so on. All right? But in quantum field theory, as properly done, we have to enforce these operator commutation relations. And so that gives us, I'll talk about later, much of what we think of as sort of quantum behavior. No, so if you insist that things are classical, of course you get wrong answers. Okay, so that's not my position.
From quantum field theory, a coherent state, in a classical state.
You won't get clicks then, because a click is a number measurement, and a coherent state is a state of indefinite number.
If you put a laser beam through a beam splitter, I'm going to get 2 beams.
Right.
So what's different?
Well, because you're familiar with number phase uncertainty. If you, there's is there a place I can write here? So that commutation relation gives you a, and there's a plus or minus, I can't remember there, but it gives you a number phase. So this would be a measurement of complex phase, and this is a measurement of number. And they're incompatible. So as soon as you do a click measurement, you're measuring number, which means now phase has become indeterminate. Okay, so a coherent state with a definite phase, by definition, does not have a definite number of particles. Okay, so it's really just saying, just as we have position momentum uncertainty, and you can't get a definite measurement of both. In the same way, with the coherence, with any optical state, you can't get both a definite number of a measure of number and a definite number of the complex amplitude, because those are incompatible by this commutation relation here. Okay. So again, the overall perspective is not to insist on classical waves, because clearly classical waves do not explain things. What I'm saying is that the underlying many-body wave function is ontologically real. All right, and it's a thing.
Why are you saying this? Because the water waves are real.
Yeah. Essentially, I'm saying, okay, that phonons, photons, and electrons are all quantized the same way. All right, and I take the perspective that we know that classical waves are just the large n limit of boson waves. Right? Right.
And so that's why we say we actually abstract all quantum phenomena there. That's why we say it's real. Now, if you say the water wave is actually the whatever coherent state, meaning I can measure maybe the uncertainty of this coherent state, I put in the Bell experiment, so then I'm not sure anymore that I can say.
Well, maybe let me just make a related statement. Sometimes when people think about a coherent state, you can write it as a sum of Fock states, of states with definite number. You write it as a superposition of many states of different number. Okay, that's because you've chosen that particular basis. Okay, But that doesn't mean that that set of basis states is the only possible set of basis states, right? And so, you know, I would say it's improper to insist, well, a coherent state is really a superposition of Fock states, okay? I would say that's one particular basis. One could write it in. And one could also write it as simply an eigenstate of the A operator. And it's a perfectly good quantum state on its own. So it's only when one tries to do a number measurement that one is forced then to deal with Fock states and all the things that come from that.
I'm just saying that this is not sufficient, and I mean, it's hard, but
Yeah.
a sufficient reason to believe that that's real because the water waves are real.
Well, okay, I will grant you that this is not a proof, okay? This is an intuition in the fact that the way that one normally proceeds in quantum field theory is that the waves are the thing, and that one can always, after the fact, if one wants, come up with exact particle states. But you don't have to be in exact particle states, and so there's no reason to prioritize those and to say that they're somehow fundamental.
So we should give you continue.
Yeah.
Just to clearly understand exactly what you want to say. So are you saying sort of that it's specifically looking for measurements that will measure the number, the eigenvalue of the number of the eigenumber of the number operator that points,
So I guess what I'm arguing against is the idea that particles are sort of favored basis, that the particle description is sort of the more fundamental one, and that the waves are less real. Okay.
do measurements in the field basis, you wouldn't have an issue with interpreting it as a real wave.
Yeah. So a coherent state is a perfectly good physical state. Okay, it's an eigenstate of the A operator. All right. And as such, it has an indefinite number of particles, all right? So I would argue that it's a real thing, all right? And it's not just ontologically a superposition of something else, all right? And so I'm really saying that there's no reason to, so we can always write states in the Fock state basis of definite number of particles. What I'm saying is there's no reason to prefer that basis.
So you're saying the problem is from demanding that what real means is whether the particles that this thing is made from.
Yeah, so maybe it's an unfortunate thing in English that when I say real, I don't mean real valued. I mean ontologically substantial. Okay, so we talk about real and imaginary values, right? And classical fields are real in the sense of being real valued, but I'm using real here in the sense of echt, you know, is that it's ontologically physical.
So you're saying that the correct ontology is not the particles, because you're saying, look, this thing is real, it just has an indefinite number of particles.
Right.
Don't care. So you're saying that ontologically the particle picture is wrong.
Well, I'm saying the particle picture is one of many bases one could use, that the particles are not favored.
Ontologically meaningful and indeterminate, right? So you have to let go of the particles. You want to take the field as the.
Well, okay,
Yeah, that's what I'm asking.
yeah, so we should probably move on, but let me just say, in some sense you could say a field is a thing, all right? And now you can say, how should we describe that mathematically? As soon as you do that, you have to say, what basis should we use, all right? And so then you say, well, one possible basis is the set of Fock states, okay? That's one basis I could use, but I don't have to use that. I could use other bases of different eigenstates, and there's no reason to prefer the particle basis over other possible bases. What's that? No, I'm saying there's no preferred one. I'm saying the field. So maybe again you could say, yeah, we've got a state, okay, and then I could define it in some basis or another, right? But I don't have to. I'd say this is a thing, all right, and I could pick different bases to represent it in. All right, let's move on. It's a really good discussion, though. I really. We'll have to have some of these discussions over coffee. Okay, well, I'm allowed to go past noon, right? All right. All right. This probably also bothers some people, but I'm going to just throw these out there for you, all right? 2 experiments that have nothing to do with the existence of particles. What they do have to do is with that commutation relation I told you, okay? One of them is the photoelectric effect. You can derive this completely with a Bloch sphere model with a continuous transition. This has been shown experimentally. Good friend of mine in the 90s. We could literally do these experiments in my lab, but I didn't. It was a friend of mine. But you can generate all the effects of the photoelectric effect without making any statements about the existence of particles. Similarly, this is what I did on a different sabbatical way back in 2012. The entire Planck distribution can be derived entirely from field theory without any statement about the ontology of particles and without any random number generation and so on. So if you're interested in that, you can look up that paper or come talk to me. So particles, such as electrons and photons, don't have any natural length scale. Atoms do. And so, of course, lumpy behavior actually does exist in the world because we have atoms. And so atoms indeed make lumps because we have a natural length scale which arises in our system. On the other hand, if one tries to treat them as point particles, you get in all kinds of mathematical conundrums where if you try to say, if I have a photon localized literally to a point, there's a lengthy discussion. I think it's in Mandel, I can't remember, but there's a lengthy discussion about the problems of trying to localize a photon to literally a single point. So this is new. This is something that I published this a couple years ago. It's kind of cute, all right? And it's actually how to think about fermions. So one thing that you notice when thinking about fermions is there's a bunch of 2s, right? So there's 2 spin states. There's 2 allowed occupation numbers, 0 and 1. There's 2 wave function components, real and imaginary parts. There's 2 bands, matter and antimatter. And the question is, are these all related or are they all accidents? And it turns out they're all related, not surprisingly. And to understand this, you have to go back, actually think about Dirac. If you go back to his very early versions of his quantum mechanics book in the 1930s, when he derived the Dirac equation, there's 2 things that he wanted to do. One of them was to have relativistic equations of quantum mechanics, of course. But the other, which is less well known, is that he felt very strongly that particles with mass should have a non-zero probability of being detected at all times. They shouldn't wink out of existence. Now, what do we mean by that? Well, if you think of a bosonic wave, it's like a spring-like motion. And so there is, for every bosonic wave, there is some instant in time when the amplitude is 0 everywhere in space. And at that point, there's 0 probability of finding the particle if you take the wave function as being a probability amplitude. Well, that bothered Dirac. He felt particles with mass, you should have mass conservation at all times. And so you shouldn't ever have a time when there's no particle. And so he noticed that there's another way to have periodic behavior, which is circular motion. And in this case, you have, it's represented as a phasor going around the complex plane. And then the amplitude is constant because it's a circular motion, but you still have this oscillating behavior. And of course, in introductory physics, we often use this as a model for bosonic behavior and say, well, you can project one onto the other. But his argument was we needed to preserve this, sort of circular degree of freedom for fermions. And so putting the 2 together is what led him to his Dirac equation. And there's an appendix in my book that discusses how he did that. I'm not going to go into the math of it. Just to make a couple observations. One is the Schrödinger equation gives circular motion always in the same direction in the complex plane. You may have noticed that. And of course, that amplitude is constant, which is what made Dirac happy. So in putting these together, first of all, in order to have it be relativistic, he needed to make a 4-vector. And so to do that with fermions, he came up with the idea of having 2 bands, each with a spin degeneracy, so that you've got matter and antimatter bands, each of which has a plus or minus state. And that gives you a 4-vector then. So that immediately led to the prediction of antimatter. Was one of the great successes of theoretical physics, where a theoretical concern immediately led to a beautiful experimental observation. But going back to the fermion 2s, this is a cute little mathematical trick, which is you can take these same A operators, now they're fermions, right? And we're going to write them in terms of spinors, where the spinor is acting on the 2 states which are n and 0. Okay, so it's basically a rotation between the 0 and the 1 states. So now we have n equals 0, no particle, n equals 1. Okay, and now you have 2 real and imaginary axes here. And so what you find is that the n equals 1 state corresponds to regular Schrödinger rotation in the complex plane. And the n equals 0 state simply corresponds to rotation in the opposite direction. And that they're really just mathematically slightly different based on, again, a minus, plus or minus sign here, giving rotation in the 2 different directions. Now, it also is true for antimatter, but in the case of a antimatter state, an occupied antimatter state is rotating in the opposite direction. One of the nice things that falls right out of this is that if these are now, again, the spinor matrices that I defined for now acting on these 2 states, you immediately get that the commutation relation for the A and A dagger, which are our standard creation and destruction operators, immediately falls out that that has to be the statistics that gives us the fermion statistics. And so you can see the fermion statistics here, the anti-commutator, just coming out of the fact that we've got a circular motion and 2 degrees of freedom that it's rotating between. The implication of this for philosophy is that the n equals 0 state is just as ontologically real as n equals 1. It's really hard to insist that rotation clockwise is a real thing and the clockwise, counterclockwise is the absence of something. Yeah.
Sorry, but where was this temporal evolution in the first place? Like it was just sigma operators. I didn't understand where it comes to rotation in the first place.
Well, okay, so you have, in general, a Hamiltonian, which is, n is equal to h bar omega times n, where this is A dagger A, right? So there's some associated energy, where this is, there's an associated omega k. So for any, sorry, this is...
Now we have just one speed, not alpha. In your example, with the previous slides.
Right. So this rotation is not talking about the spin degree of freedom. Okay, the spin degree of freedom that we think of as spin is coming out of the relativistic 4-vector that Dirac made. Okay, but I'm saying for a given k and spin, okay, we still have 2 other degrees of freedom, which is the 0 and the 1 state. Okay, and what I'm saying is that's one basis, which is the 0 and 1 basis. Okay, in which case that would correspond to rotation in the complex plane. On the other hand, I could pick a different basis and pick simply the real and imaginary components as my basis, okay, in which case that's the basis that these guys are acting on. And so I can switch between the 2 pictures. So again, I'm sort of disfavoring the number picture as being somehow essential, all right? And in fact, you can see if I pick the basis of real and imaginary components, then the 0 and 1 states are simply 2 different superpositions of those 2 real and imaginary components. So again, this is all sort of just to decenter particles to some degree, to say that the n equals 0 state is just another resonance of the fermion field. There's 2 resonances, the n equals 1, the n equals 0. And the energy difference between those 2 is the energy of the particle in all of this formalism. Okay, how are we doing on time? Oh, we're still doing okay on time. Okay, so now I'm going to just say a little bit about comparing interpretations. And a lot of this, I'm sure, is very familiar to you, but I have a couple remarks I want to add. So Copenhagen requires explicitly non-unitary dynamics. So unitary dynamics would say that if I have a superposition of states, then at all later times, I can always write the solution as the sum of the two solutions of either of them separately. When we do measurement, as is taught in typical quantum mechanics books like Cohen-Tanuji, that is non-unitary. You're truncating and you're getting just one of these and cutting off the other one. Now, in Copenhagen, that's simply done by fiat as a sort of axiom. So Cohen-Tanuji presents it as an axiom of quantum mechanics. But a lot of philosophers have been bothered by what does that mean? Like, what are we physically doing that actually makes a measurement? And as I said, it cannot simply be interaction with a macroscopic quantum object, because if you believe that those all are made of quantum particles, then they are also unitary in their dynamics, and so they can't give you non-unitary behavior. On the other hand, at my university and at Pitt, there's a very well-known many worlds guy, David Wallace, and there's, in the philosophy world, I would say, increasing number of people who would advocate for the many worlds approach. And actually, in one sense, it's a very simple assumption, which is simply there is no non-unitary behavior, so that everything simply evolves forever in a unitary fashion. And these wave functions can be as large as you like. And so the cats in the Schrödinger's cat experiment never collapse. I'm just going to throw out two objections, or at least problems, that are not often considered with many worlds. Of course, there's all the philosophical things about what does it mean to live as one of a million or a billion copies of yourself, but I won't get into that. One of the things that you can show is that the Born rule is not derivable for our experience within many worlds. Because if I'm in a universe which has a large amplitude wave function versus being in one with a small wave function, my universe still feels completely real. I don't know that I'm in a universe with more weight or if I'm in a universe with less weight. I'm inside it. So essentially, the overall amplitude of your whole universe wave function is not knowable to you. You can only know the things inside your universe. So this leads, so then you say, well, how would somebody deduce statistics? Well, you'd have to say, on the path that I'm following, how many branches went one way and how many branches went the other way, and I would count those up. And I would not have access to the overall wave function amplitude of each of these paths. And so you have to, in many worlds, assert as an additional empirical postulate the Born rule. And now it's not a rule of collapse. It's a rule of our experience in traveling through timelines. But it's an empirical one nevertheless. Now, another thing which may or may not bother you, I say it bothers me as an experimentalist, is simply, why don't we see all these other worlds, right? Well, if everything is strictly unitary, then we don't expect to see them. But you still say, there's an awful lot of universes out there we're not seeing. Shouldn't we expect to see them? That's a philosophical comment about no-seeums. I think I'll just skip over that. Here's my general bias again. It's not a proof, it's a bias, which is that unitarity is a type of linearity. It says that the time evolution is perfectly linear. And our experimental experience is that linear assumptions often are good first approximation, but they always break down. In any of our real experience, nothing is really linear at the end of the day. The many worlds theory amounts to an assertion that the world is strictly linear to the billionth degree, and there is not one speck of nonlinearity, because if there was, we would see these other universes. They would have effects in our universe. The analogy I have is of crosstalk. You know, if you have a radio and everything is perfectly linear, then you could tune as close as you want to one channel or another and not pick up the other radio station. But if you have a crosstalk or nonlinearity, you pick up signals from the other radio station. So one way to pose this is to say, there's an experiment we can do in my lab. Do a million counts of a photon counting experiment where you can either go to the left or to the right at a beam splitter. All right, I'm going to count 1 million photons in about a second. Now my particular world has a spectral weight of 2 to the 1 minus 1 millionth relative to the rest of the universe for my particular path. Okay. In other words, in engineering terms, the signal of my world has just been reduced by 6 million decibels. And a typical engineer, if you say, could you recover a signal that was suppressed by 6 million decibels, they would just laugh at you, right? You can't, you know, typically, you know, 100 to 1,000 dB noise suppression is considered pretty good. Anything below that is going to be lost in the noise. So another way to put it is simply that the many worlds approach plus the empirical observation that we don't see these other worlds amounts to an extremely strong assumption of perfect linearity. Because if there wasn't perfect linearity, we would see at least some vestige of echoes of all of these other universes non-linearly interacting with us. Yeah?
But didn't you just say that if it's 6 million dB, you wouldn't see it?
Right.
So why does it have to?
No, I'm saying that if you're in the one that's the 1/6 millionth, you would see the other ones, okay? You would see some effect of the larger weight ones, the other things happening around you. Okay, so I have another, I don't know if I put it in here, but you know, one of the things that some people pointed out is, you know, so here's another thought experiment. Suppose that we did a Schrodinger's cat experiment, only instead of a cat, we have nuclear weapons and we fire them at the moon. And if the photon goes to the left, we blow up the moon and the pieces of the moon fly apart, okay? And if it goes to the right, we don't do that, okay? Then you're really in the position, if you're a many worlds person, of saying that literally around you is half the moon flying in a different direction and you have no perception of that whatsoever, even though, you know, it's this large gravitating object. And so that's only true if everything is absolutely strictly linear, all right? Okay. All right. So that's all sort of just, and I'm going to skip this for sake of time. It's another way of simply saying the same thing, that if you want to localize things in one place and another in the other, it all comes down to just phase factors, right? That having them in these 3 positions as opposed to 3 over here is written on the same set of basis states just with different phase factors, all right? And you're saying to distinguish this from that requires extreme phase accuracy, which again, if you posit that everything is strictly linear, that just falls out immediately. But if there's the slightest nonlinearity, it doesn't work. All right, so my last that I'm proposing, and this will be the rest of my talk then, is spontaneous collapse. And as I said, local hidden variables are ruled out by experiments, but non-local hidden variables are not. And there's actually been quite a bit of work by other people on this. So I will just say non-local spontaneous collapse is the least exotic philosophically. I wouldn't say that the other ones are ruled out. But it requires actually altering the equations of quantum mechanics, and we all know they've been very, very successful. So the question is it possible to come up with a spontaneous collapse that's quantitative, that actually agrees with the vast body of experiments that we've done, which are out there? Well, I will just say it's not off the table to start. You know, it used to be, when I started out in physics many years ago, the Standard Model was viewed as one of the most proven theories of all time. It still is in many ways. But it allows no nonlinear oscillations between neutrinos. And then they found too many neutrinos coming from the sun, and that led to positing new nonlinear terms in the Standard Model, which allow neutrino oscillations, which then are off the books of the Standard Model. Okay, so it's non-Standard Model physics, and this is now mainstream. The same thing, the famous story of Einstein's cosmological constant, where first he proposed it, then he retracted it, and now we're back to opposing it again as something that can go in the equations. It makes them, in some sense, uglier, but it also makes things agree with the experiments more. So there is precedent for taking theories and tinkering with them even after they've been established for a long time. All right, so let's move on to actually talking about spontaneous collapse. A lot of people, when they hear spontaneous collapse, assume that I am proposing what's called a GRW approach. One of the basic criticisms that have this approach is that they're committed to the ontological existence of particles. And so they will basically have a picture of a particle moving through space. It has an associated wave function, and then that wave function collapses down to some small Gaussian randomly every so often. I just went through a lot of slides talking about how I don't view particles as favored. And so that is a general approach of theirs that I don't take. There are some significant drawbacks. When you take a wave function and collapse it, you've made all the wave functions shorter. So you've put energy in the system. So spontaneous collapse should lead to non-conservation of energy. And there's a recent experiment that went to look for that energy and concluded they couldn't see it, that there was, it's also problematic to have this constant heat source, right, of things collapsing all the time. So that was also experimentally checked. There is no, as far as I know, many-body version of this. They essentially keep track of single particles, and so they distinguish histories of single particles, and you're saying this particle is moving along, its wave function spreads out, then zoop, it goes back in again, and they're very much keeping track of distinguishable particles, and so they don't keep in track the indistinguishability. And finally, it happens randomly, whereas our general experience is that measurement is associated with decoherence. That without decoherence, things propagate in a nice quantum way for really, really long periods of time. And I don't have to tell this place that is true. And so, again, so there's multiple objections that I would find to this approach. Now, there's another sort of pair, Penrose and Diossi, who actually don't propose a mathematical model at all, but simply work from the other side, both being experts at general relativity, and arguing that general relativity can't work. General relativity can't work if you don't have spontaneous collapse. So they're not actually proposing how that happens. They're simply saying that if there isn't spontaneous collapse, you can't define the local curvature. And for the reasons that I said, basically, if I've got a superposition of half a moon going here and half a moon going here and another one where it's together, like that changes the local metric of space-time. And a superposition of these metrics becomes very tricky in GR. And, I'll just mention this as a third one. This is called the transactional approach. And I have some critiques of this online. But they basically argue for backwards in time traveling advanced waves. All right. One final motivation, then I'll give you the proposal. In general, we know we can get clicks from classical systems. Right? So just the fact that you get clicks alone is not sufficient to say it's quantum. All right? So this is a paper in which this is a completely classical system. This is laser mode hopping of two different modes of a laser, classical wave. And there's two things in the system. There's noise and there's nonlinearity. All right? And you get these jumpy clicks like that. This is a very classic experiment. I didn't put the reference down. I don't remember it. But this is looking at a single atom in a trap jumping, emitting and absorbing photons. Again, just to the eye, you'd say, well, just the fact of clicks is not itself proof of that you have, some kind of knowledge-based behavior. All right. So what is the approach then? The easiest way to think about it is to think of the block sphere. And now remember, I said that the n equals 0 state of a fermion and the n equals 1 state of the fermion are two states. And so I'm going to put the n equals 0 down here and the n equals 1 up here. And now I'm going to allow rotations on this block sphere, all right? So that we can now precess not just in this plane, but in this plane here. So that now the particle can move between the n equal 1 and the n equals 0 states. And again, that's easier to visualize if you remember what I said about fermions, that I don't have to pick the n equals 1 and the n equals 0 basis. I could also pick the real and imaginary components, right? So that I can simply view these two states as the n equals 0 and n equals 1 states. So now I'm going to write a superposition which is a definite n equals 0 state at the bottom of this and the environment of the system which has the extra fermion. So both of these terms have the same number of total fermions. Okay? In this case, the fermion is out in the environment, the extra one. And here it's in the top state, and so the environment has one less fermion in it. Okay? So total number is conserved here. And of course, that happens by standard interaction terms, which are fermion number conserving, right? So you might have a fermion hit something, bounce off, and go into another state, exiting and going to the environment for that matter.
So
yeah.
that means that I will not be able ever to measure alone just the second degree of freedom in 0 plus 1 basis. Because this will not conserve the number of fermions.
Yes. Yes. So this is a strictly number conserving term. Yeah.
So what is the meaning then in dividing this Hilbert space into two parts if I cannot independently manipulate one part of it?
I think, well, I mean, so I hate to say never because maybe somebody could come up with a clever experiment that I haven't thought of, okay? But I think what it does for me is, I mean, I'm just switching bases, right? So you're saying I've got n equals 1 equals 0 perfectly basis. I'm just doing a mathematical trick to put it in another basis, okay? What that does for me, though, is it simply says that the idea of a rotation between 0 and 1 is not some kind of fantastical idea, right? That I can put in a term that induces that rotation. Okay? It's mathematically possible. Okay? And again, now this is a normalized state here. Okay, so what's going to happen then? So I'm going to write this in terms of block vectors. And so we have U3, which is the vertical axis here. It's going to tell us the probability of finding it in the upper one and lower one, if you want to think about it that way. And now I'm going to introduce a Rabi frequency. So I'm going to introduce so there's one frequency, which is the precession in this plane, which is your standard precession, and that's just the actual h omega of the state, right? And then there's another one, which is the Rabi, which introduces Rabi flopping between these states. And I'm going to make that proportional to phase fluctuations of the rotation in the plane. So if everything is stable and is just sitting there in vacuum, this goes to 0 because I have a time derivative. And if there are glitches causing the phase to shift, okay, that will lead to windings in this way. So I'm saying that environmental fluctuations that are time dependent will lead to a precession of Rabi flopping type behavior in this vertical direction on the block sphere. Okay. Now, I'm going to do one other thing, which is I'm going to make the endpoints attractors. So I'm going to multiply this by this factor, which is basically the magnitude in the perpendicular direction, so that if it gets to either 0 or 1, it's going to stick there. All right? So because that will simply, the square term will go to 1, and so therefore there'll be no Rabi flopping there. The only way you could change to a new superposition is by a standard Schrodinger term where you have an actual interaction that leads to this thing bouncing away in some way. Go ahead. Omega n is the precession in the plane. Okay.
Are you considering this to be stochastic?
What's that?
Are you considering this to be stochastic, the rubber flopping, or coherent?
So what I'm arguing is that the stochasticness comes from the local environment. So I'm saying there's actual local fluctuations that are giving kicks.
So it's not a coherent rubber flopping.
Well, it might be coherent for a time, but that it is essentially going to be, my next slide will actually explain that. So let me go to the next slide. So this is what we get here, which is we have random kicks. So you can think of it plus and minus Rabi kicks, which are greater or larger in magnitude depending on what the local environment is doing. And so what you get is a random walk on the U3 axis. And eventually it will hit one of those and stick there based on this term. What's interesting is that now I can do this actually numerically and do many, many instantiations. And you reproduce the Born rule perfectly. So that you say, if I go back to my block sphere, my initial position on this axis is would be interpreted as the probability of hitting this or that, right? So if I'm at 70% here, right, that says it's 70% likely to hit this and only 30% likely to hit this. What I'm saying is numerically, if I started at this point and I run a random walk, it actually reproduces the Born rule perfectly. It comes out and gives you the right statistics so that if you start it there, it's 70% likely to hit this and 30% likely to hit that. Now, I did this numerically, and then I started talking with a mathematics graduate student who actually just in the last couple of weeks came up with a proof that it has to be true because this is an example of what's called a martingale random walk. And so the probability of hitting one of the two boundaries on a random walk is exactly given by the Born rule for what's called a martingale walk, which basically means that the probability of an up or down step is equal at any point in the walk. And so that works. Okay, so here's an interesting thing is that so I wrote it down, or I described it in terms of block rotations, but when you do all the math, it turns out that it amounts to adding this term to your Schrodinger equation as an extra so-called interact energy. So it's non-unitary. It's got an I here. It's weird because it's got an expectation value, which is measuring the instantaneous wave function, right? So, and then you've got an operator here. But if you look at the overall form of it, actually looks pretty simple at the end of the day. This is the term I'm talking about adding to the Schrodinger equation. And this will give you exactly the rotations that I was proposing with the block sphere. And then if one wants, so that's the term again. It has the virtue of simplicity, no proof. It's more an aesthetic type thing. But aesthetics matter in physics. And you can switch it around with some assumptions to write it in this form, where now you're writing it in terms of standard spatial field operators. And this, again, remember, this is a fluctuation of the local energy density, which is giving you your random fluctuations. Some more appeals. It gives no collapse because it depends on local time-varying fluctuations. It doesn't give you any collapse if everything is just sitting there smoothly. It strictly conserves particle number, again, because you're basically just rotating between two states. So one way to look at this is say I've got this state, and I'm going to project by rotation, by rotating my vector onto one of these endpoints. By doing that, I remove one of these, but each of these had the same total number of fermions, and so total fermion number is conserved. And in the same way, again, with a slight bit more mathematics, you can show it also conserves total energy under the same assumptions of Fermi's golden rule, which is basically a strong dephasing or no long-range decoherence. So this is be my last slide here then of any, the rest will just be summary. The weird thing about this is actually something that goes way back to when people were thinking about Copenhagen. So imagine a standard EPR experiment where we have one detector closer than the other one. And so if we're sitting in the rest frame of this laboratory, this photon hits this detector, and we can detect a polarization of one type or the other. And then in sort of the standard narrative, you'd say, well, that then non-locally collapses what will happen over at detector 2. Okay. Well, as many people pointed out in regard to Copenhagen, with relativity, you can always boost to some other frame in which the photon arriving at detector 2 comes before the photon arrives at detector 1. So that if I boost, so in this frame, you can see that this event happens before this one. But if I boost to a different one, then this frame, this event here, which is the detection at this one, happens earlier than the detection over here. So you get into weird questions of what is called narrativity, of whose knowledge was the one that really did it. And you'll have lots of different philosophical approaches about that. Now, there is philosophers such as Myhrvold who will say, don't worry about it. It's just sort of, you get the same story at the end of the day, and so it doesn't matter. But if you think about spontaneous collapse, where I'm arguing that it really was a local fluctuation, not something meta called knowledge, then it seems to push the issue a little bit more. So one of the approaches might be to simply say there really is a favored universal reference frame. And so this non-locality really is happening. And we know there is at least one favored reference frame in the universe, which is the rest frame of the cosmic microwave background. Alternatively, one might get into GR and say that you have some kind of local frame which is attached to mass, because we all eventually want to get gravity and quantum mechanics to work together anyway. So in some sense, this is no better or no worse than Copenhagen in terms of the relativistic narrativity questions, but it's not any worse. And on the other hand, it puts some quantitative elements to it. So I'll just finish with this. In general, some people just don't like any spontaneous collapse theories. They don't like tinkering with the equations. I've given you some arguments why it's okay to tinker with equations that are long and well established, such as the standard model. But also I'd say maybe it's just partly because we've all learned Copenhagen so much that it doesn't seem as weird as it ought to. Like you're really saying the same thing in Copenhagen, but you're saying it's a mechanism that's off the books. And it's just as kludgy as the spontaneous collapse, only you've sort of cleaned it up and just made measurements somewhere outside of the realm of your thinking. So I would say, given the philosophical conundrums of some of these others, any spontaneous collapse theory that works should be favored. On the other hand, what's not clear is whether it works, right? So I've shown you, I've worked out a bunch of examples where it works, but quantum mechanics is large, right? So it may be there's an experiment somewhere it doesn't agree with, or a prediction for an experimental test we haven't done yet, which would make it falsifiable. I don't know the answer to that. So it might be that this particular model doesn't work, but and then I would just challenge people to find another one that does, because there's a lot of details in this model that could be varied or changed, especially what's happening to the Rabi frequency, what actually leads to that rotation in the local environment. So I'll just finish up with this then. This is a start to a quantitative theory. It's not fully worked out with all possible experiments, but I think I would like to see some people challenge me, tell me why it doesn't work. And in general, I would just argue, as I have, that spontaneous collapse is, to me, philosophically preferable if you can make it work out. So I'll finish with that. Thanks. Yeah, so I'm saying this is, so this is what I'm saying, at core, every measurement begins with either or, right? And so you have a cascade type effect in a typical detector, but somewhere along the way there had to be a fermion that actually like committed to being, popped out of an atom somewhere. Well, what I'm saying is sufficient to, so actually it's a whole other topic. So actually, my experience is almost entirely in bosons because I'm a condensate guy. And there's an equivalent weird thing in bosons, which is a whole other talk, which is that how to get coherent states, right? Because it turns out that you can't get a coherent state unless there's some tiny bit of spontaneous symmetry breaking. And some people will say, well, that happens due to measurement. And other people will say, maybe there's some tiny nonlinear term like what I'm proposing. It would have a completely different effect in condensates than what it has here. So what I'm saying is that the measurement we're familiar with can be explained just with fermions. There could be an equivalent term in bosons, but it would have a different effect. It would actually lead to the appearance of what I'm talking to you with right now, macroscopic coherent waves. So one can argue, and this is a whole other talk, that there is a spontaneous symmetry breaking due to a nonlinearity in bosons that leads to collapse into actual coherent states. That's a whole other talk. Yeah.
Probably this is pushing it a bit too far, but when you had this example of like nuking the moon and we should be feeling somehow the effects of the other branch where it has been nuked or not.
Where the moon has been blown up?
Yeah. Could we make the same type of argument for all our structure in the universe? Because our current models say that our structure in the universe comes from quantum fluctuations. So we should have many other universes with a completely different matter distribution. So why don't we feel that already?
So you're talking about, so there's sort of two different versions of many worlds. There's sort of the quantum mechanical, in this world, we have a superposition of many ones. And then there's the many universes model, which is cosmological, where you have bubbles, floating all around. So the first one, definitely the same argument would apply. That if you've got one universe where Jupiter's over here and another where Jupiter's over here, how do you define a gravitational metric for that superposition? That's problematic for GR, as people like Penrose have pointed out. So yes, it's also true. Now, the many universes thing is like a whole other thing, and I'm not really going to comment on that.
And then shouldn't we be more inclined to not pick the first one and rather say, oh, maybe we don't need to have like one metric for superposition, right? We just have different metrics in superposition and we don't have the problem, and the problem seems to be...
It depends on how you are trying to unify gravity and quantum mechanics, because the metric plays a role in what you think is forward in time, right? And so forward in time goes into collapse, right, and irreversible things. And so even, again, many worlds still has to worry about that because there's my personal timeline of what I experience, right? And so is that affected by the existence of some large gravitating object in a parallel universe? Like these are interesting and difficult questions. Yeah.
Does this non-local spontaneous collapse make predictions that are different from Copenhagen interpretation, or do you expect it to?
That's a really good question. So in general, by putting it on the books, it makes it open to different predictions that could be tested. I spent a fair amount of time thinking about that, and what I could say is that essentially all types of random walk give the same Born rule. So we have these random walks. At first I thought, well, maybe if it's a Gaussian step, or a Lorentzian, like you could tell the difference between those. It turns out, again, by this theorem this math student showed, that any martingale walk where up is equally probable to down, it doesn't matter the details of how it's picking those steps. It'll always give you the same statistics. That doesn't rule out there's something I haven't thought of, though. So I would say it's an open question whether it could be experimentally tested. But it puts it in the realm of physical reality so that that's not a crazy question to ask. I guess I would go one step further to say, though, that given my philosophical biases, if a consistent framework can be made, which is self-consistent, even if it gives no experimental predictions, I would still favor it because of the less philosophical baggage. It'd be great if it had a falsifiable prediction, which we could, actually do. But I would say if you can show that it works, even if it makes no predictions, it's still favored in my view.
What is the environment then?
What is the environment?
Yeah.
Anything that, basically, so if you think of an atom, right, anything that's bonking it around and causing the local energy density to go up and down. And so that is going to be inhomogeneities fluctuating.
If you put something in the lowest vacuum, you can imagine floating, in thought experiment, put something in complete vacuum.
Yes, then this would say there's no dephasing. That basically, so you guys are familiar with this language of homogeneous broadening and inhomogeneous broadening. Okay, so this is sensitive to inhomogeneous broadening. Okay, so that if there's actual fluctuations of the local environment of any type, they will all give this behavior. If it's sitting in vacuum, it doesn't decohere, and so this doesn't give any collapse in that case. So my argument is that all real detectors have local fluctuations that are actually bonking the electrons around.
Any predictions about gravitational?
No, well, only in the sense that Penrose and Diosi have already said if you don't have spontaneous collapse, you cannot write a consistent gravitational metric. So I will just take that as a supporting argument, but I'm not making any arguments the other way as to how to write the metric down.
I have a couple of questions.
Uh-huh.
So if I have a very large quantum system, so with many particles, but no detector, then there is no collapse. Of what? Of a subsystem of that or of the whole system?
So it would be, so again, you would have electrons actually committing to one state or another. So that it basically amounts to a projection out of the whole many-body state. Now, what's interesting, this again gets back to my day job. So I did a lot with Boltzmann equations, quantum Boltzmann equations, to model the time dynamics of things. So a quantum Boltzmann equation, you start with many-body quantum mechanics, and you derive irreversible behavior. And you say, how did we do that? It's a unitary system. And it turns out if you couple any small system to a large system, you guys all know this, right? You get information spread over these many degrees of freedom, and it's effectively lost forever, right? In the numerics, that corresponds to essentially truncating your wave functions and projecting them down all the time. So that if I am numerically running the quantum Boltzmann equation, and I think about like a density matrix, and I keep the diagonal element, so in a quantum Boltzmann equation, you have a very large density matrix with many positions for all the particles, or all the states. And you keep truncating by throwing away off-diagonal information and only keep in diagonal information, which is the occupation numbers. Well, essentially, that kind of truncation is exactly what this is doing actually physically. Like, so in the quantum Boltzmann equation, you're doing it as a numerical simplification. You're simply saying we're going to throw away all this phase information because it's all kind of small anyway, and we're going to just keep the diagonal information. This is actually saying there's a physical process by which off-diagonal information gets thrown away.
But this is through the coupling to the larger system, am I right? Which you call environment.
Yeah.
But the whole environment and this system still coherent, quantum mechanical. Is it true?
If it's homogeneous, right?
If it's, let's take homogeneous.
The whole thing is subject to time fluctuation.
Let's take it homogeneous.
Right. So if it's perfectly homogeneous, then it stays coherent. Yeah.
Okay. So it's
So
not.
if I have a gas, like a time unvarying, gas in a box.
Okay.
Right? Some people talk about the eigenstate normalization hypothesis. That it's going to stay sort of in that state as an unchanged state.
So there is no problem, I mean, with having very large system perfectly coherent within your model. Okay, and then this is kind of a modeling of detection itself, of detection of a system. But now,
it doesn't mean somebody has to be there looking at that.
no, I understand. There is a detector, doesn't need to be anybody. Okay, so then there are things in the nature that you call detectors. Because if I think about detector as one part of the system, and you just said that if it's everything non-homogeneous, and I can think about the special state of a detector to be homogeneous, then I can have a quantum system, environment, and even this detector, all homogeneous, then there will be no collapse.
Yeah, so I'm arguing that real detectors have actual fluctuations going on. So that the stochastic element in my theory is from actual random motion of things spatially.
Okay, and that's what's called detector then. The piece of matter that's called detector has this property.
Yeah, so detector would be an avalanche mechanism connected to some kind of temporal fluctuation.
Okay, good. And then I have two small, one comment and one question. So your theory is nonlinear. Am I right? Like nonlinear in the wave functions.
Here, right? So it amounts to adding this term.
Yes.
Right?
But you're aware of these old problems with nonlinear, that they can produce signaling on distance.
Can produce what?
Signaling on distance. So.
Well, that's an interesting question. Too.
Like.
So could one find a way to use this to make predictions for physical experiments? And if so, would it allow you to have some kind of...
There is a very general result by Nicolas Gisin that nonlinearities produce, for the pure states, if you have nonlinearities, they will always produce signaling, unless you have a noise term that suppresses the signaling.
Yeah, so I'd be really interested in seeing that paper because I've thought about that. I have not seen the general proof that this particular type of nonlinearity falls into, but I don't know that paper. So
okay.
I'm interested in seeing that.
And the last, what are the what is the scale of like number of particles, or what are the free parameters of the thing that you have?
Yeah, so one of them here is right here. Where's that? So this tau is a free parameter, right? So you're saying that there are some phase glitches in this rotation, okay? How much winding in the vertical direction does that cause? There's a concept of proportionality, and that's a parameter. So I can say it's small, right? But that's definitely a subtle.
But when you have this number state, number operator, can I take some very small number operator and then suppress the... sorry, state that for which when you evaluate the number operator, you have a small number, because you have n as well, am I right, in the nonlinear part?
Yeah. So you're saying like...
Can I take some states, size of the state to be small?
How big could the state be?
Yes.
Yeah.
Does this influence the time after which you have a collapse?
So I think that, so when I wrote down this here, I talked about how going from this to this requires a coarse graining approximation, where you say that things are basically, because you have to be able to take this guy outside of the sum in order to get this, okay? That amounts to saying that there's a typical size in which I'm defining my eigenstates, all right, over which my fluctuation outside of that is constant for that whole region. So that could be, you handle that in two ways. One is you could actually say there is a natural length scale, such as the size of an atom, over which this is true. Or you could argue that if it's not true, it leads to correction terms to this, and it leads to higher order things going on that might have to be accounted for.
Okay. Yes?
Does your model differentiate between the massive particle and electromagnetic wave? I mean, is these two parameters actually affect the same rate on the collapse model, or they are the same things actually?
So the state
So if it is a massive,
for this kind of rotation for photons. Right? This is a very fermionic thing, okay, that requires a sort of view of a fermion as kind of a rotation between two eigenstates.
So because I was wondering if you have a massive catastate or with a mass or electromagnetic wave catastate. Which one is more
What comes in here is the fermion versus boson state.
Okay. So thanks.
Okay, I think we can conclude. Thank you very much.